Our paper is titled FJMP, Factorized Joint Multi-Agent Motion Prediction over Learned Directed Acyclic Interaction Graphs, which is joint work with my colleagues in the WISE lab at the University of Waterloo. This work explores the task of multi-agent joint trajectory prediction, which is the task of predicting joint behavior of multiple agents in a driving scene, which requires properly reasoning about interactions between agents. In our work, we propose a joint motion forecasting framework called FJMP, which factorizes the joint prediction task over a learned directed acyclic interaction graph. The video shown here illustrates the factorized decoding procedure that is implemented by FJMP. We show that FJMP produces better joint forecasts than non-factorized baselines that better reasons about multi-agent interactions. Let us now explore FJMP in more detail. For context, prior work in joint motion forecasting produces joint predictions simultaneously for all agents in the scene. Instead, we factorize joint prediction over a learned interaction DAG. An interaction DAG describes the influencer-reactor interactions between agents in a driving scene, where agents are represented as nodes and their interactions are represented as directed edges. For example, the DAG shown here indicates that Agent 1 influences Agent 2 during the future prediction horizon, as there is a directed edge from node 1 to node 2. Given a learned interaction DAG, we can factorize joint prediction as follows. We first produce marginal predictions for the source nodes in the DAG. Then we step through the topological order of the DAG and produce conditional predictions for the next set of agents, which condition on the predicted future of their parents in the DAG. We continue this process until all agents have a predicted future. The resulting scene-level prediction is what we refer to as a factorized joint prediction. To implement factorized joint prediction, we propose a joint motion forecasting framework called FJMP. Let us now look at each component of FJMP in detail. FJMP first encodes the HD map and agent histories to produce map and interaction-aware agent features using a lane GCN style feature encoder. Moreover, FJMP has an auxiliary non-factorized joint prediction decoder, which is only used during training. This is used to regularize the agent features so that they are future aware. In other words, they are predictive of the future. We use the future-aware lane GCN encoded features to initialize a graph neural network that predicts the interaction graph. The interaction graph prediction task is formulated as a multi-class classification task on the edges of a fully connected undirected graph, where each edge can take one of three labels. For example, for the edge between the blue and green nodes, either blue influences green, green influences blue, or no interaction exists between the agents corresponding to the green and blue nodes. The softmax scores on each edge can then be thresholded to produce a predicted discrete interaction graph. As we require a DAG for factorization, we additionally prune cycles using a classical cycle enumeration algorithm called Johnson's algorithm. To supervise the interaction graph prediction task, we derive heuristic labels by taking inspiration from the concept of conflict areas. Namely, if two agents occupy the same conflict area in their ground truth future trajectory, we say the two agents are interacting, and the influencer agent is the agent who reaches the conflict point first. For example, red here is the ground truth past, and green is the ground truth future of agents M and N respectively. And they both occupy the same conflict area, and since the yellow agent, agent N, reaches the conflict area first, the heuristic label assigned to the edge between M and N is N influences N. Finally, given the future-aware lane-GCN encoded agent features and a predicted interaction DAG, we can now perform factorized trajectory decoding as follows, where we use a size 3 DAG for ease of explanation. We first predict associated marginal predictions for the source node agents in the DAG. These are the green and orange agents. And we encode these features with an MLP. Then, to predict the future of the blue agent, we aggregate the encoded futures of blue's parents via graph attention, and fuse this aggregated information into the blue agent's lane-GCN feature representation using a GRU. This process will fuse the conditional context about the predicted futures of the parents of the blue agent into the blue agent's feature representation, allowing the network to facilitate conditional prediction of the blue agent. FJMP ranks first on the multi-agent interaction benchmark, outperforming all other methods in minimum average and final displacement error, as well as the ranking metric consistent miss rate. All other competing methods are non-factorized, which demonstrates the benefit of factorized prediction. Moreover, we study the effect of factorization by comparing against a baseline that produces simultaneous joint predictions instead of factorized joint predictions. FJMP improves over the non-factorized baseline across both the interaction and Argoverse 2 datasets. It improves most substantially over the interactive agents, which is measured using the interactive minimum, average, and final displacement errors, where the displacement errors are measured only over the agents with an incident edge in the heuristic ground truth interaction graph. Finally, we show a qualitative result, where FJMP better handles the joint prediction of an interactive left turn scenario. Namely, the left turn mode is not correctly predicted by the non-factorized baseline, but is correctly predicted by FJMP, as it can reason more appropriately about the influencing agents, namely 1 and 2, when predicting the left turn agent 0. Thank you for listening. Please visit our project page and check out our poster for more details.